Good morning, dear student. Today we have a next lecture of our course, Formal Language, Automata and Codes. And I told you that I have a problem with health. I have a very strong inflation, and if you listen that I have a problem with my voice, and maybe some problem with reading of the lecture. So we shall start. And today will be lecture number 6. And this lecture will be devoted to the equivalence of the deterministic and non-deterministic finite acceptors. So we shall start. We now come to a fundamental question: in what sense are deterministic finite accessors and non-deterministic finite accessors different? Obviously, there is a difference in their definition, but this does not imply that there exists any essential distinction between them. To explore this question, we introduce the concept of equivalent between automata. So, first definition: two finite acceptors M1 and M2 are said to be equivalent if the language which is accepted by the first automata M1 coincides with the language which is accepted by the second automata M2. That is, they both accept the same language. As mentioned, there are generally many acceptors for a given language. So any deterministic finite acceptor and or non-deterministic finite acceptor has many equivalent acceptors. Example: the deterministic finite acceptor shown in following figure. Yeah, we have input states and which is output states is equivalent to the non-deterministic finite acceptor in the following figure. And because they both accept the language, which consists of the following words: 1, 0 in the power n, where n is positive integers. When we compare different classes of automata, the question invariably arises whether one class is more powerful than other. By more powerful, we mean that an automaton of one kind can be achieve something that cannot be done by any automaton of the other kind. Let us look at this question for finite acceptors. Since a deterministic finite acceptor is a sense a restricted kind of non-deterministic finite acceptor, it is clear that any language that is accepted by a deterministic finite acceptor is also accepted by some non-deterministic finite acceptor. But the converse is not so obvious. We have added non-determinism, though it is at least conceivable that there is a language accepted by some non-deterministic finite acceptor for which in principle we cannot find a deterministic finite acceptor. But it turns out that this is not so. The classes of deterministic finite acceptors and non-deterministic finite acceptors are equally powerful. For every language accepted by some deterministic finite acceptor, there exists a deterministic finite acceptor that accepts the same language. This result is not obvious and certainly has to be demonstrated. The argument, like most arguments, in this course of lecture will be constructive. This means that we can actually give a way of converting any non-deterministic finite acceptor into an equivalent deterministic finite acceptor. The construction is not hard to understand. Once the idea is clear, it becomes the starting point for Gauss arguments. The rationale for the construction is the following. After an deterministic finite acceptor has read a string W, we may not know exactly what state it will be in, but we can say that it must be one state of a set of possible states, say Qi, Qj, so on, Qk. An equivalent deterministic finite acceptor, after reading the same string, must be in some definite states. How can we make these two situations correspond? The answer is a nice trick. Label the state of the deterministic finite acceptor with the set of state is such a way that after reading the string W, the equivalent deterministic finite acceptor will be in a single state labeled by the set of the previous states Qi, Qj, so on, Qk. Means for a set of the size of Q states that are exactly 2 in power size of Q subsets, the corresponding deterministic finite acceptor will have a finite number of states. Most of the work in this suggested construction lies in the analysis of the non-deterministic finite acceptor to get the correspondence between possible state and inputs. Before getting to the formal description of this, let us illustrate it in a simple example. Compare the non-deterministic finite acceptor in the following figure to an equivalent deterministic finite acceptor. So we have the deterministic finite acceptor with input state Q0, output states Q1, yeah. Our alphabet which consists of 2 letters, A and B. The non-deterministic finite acceptor starts as a state Q0. So the initial state of the deterministic finite acceptor will be labeled the set which consists of the states Q0. After reading a symbol A, the non-deterministic finite acceptor can be in state Q1, or by making a lambda translation in state Q2, yeah. Therefore, the corresponding deterministic finite acceptor must have a state labeled Q1, Q2, so it consists of the set Q1, Q2, and translation delta of Q0A is equal to the set which consists of the states Q1, Q2. In state Q0, the non-deterministic finite acceptor has no specific translation when the input is the letter B. Therefore, delta of Q0B is equal empty set. Yeah. State labeled by empty set represents an impossible move to the non-deterministic finite acceptor, and therefore means non-acceptance of the string. Consequently, this state is the deterministic finite acceptor must be a non-final trap state. So we can we have now introduced it into the deterministic finite acceptor, the state Q1, Q2. So we need to find the transition out of this state. Remember that the state of the deterministic finite acceptor corresponds to two possible states of non-deterministic finite acceptor. So we must refer back to the non-deterministic finite acceptor. If the non-deterministic finite acceptor is a state Q1 and reads a symbol A, it can go to the state Q1. Furthermore, from Q1, from the state Q1, the non-deterministic finite acceptor can make a lambda transition to Q2. If for the same input, the non-deterministic finite acceptor is in the state Q2, then there exists no specific transition. Therefore, we get that delta of Q1, Q2, and letter A is equal this Q2, Q1, Q2 as a single set. Yeah. Similarly, we get that delta of Q1, Q2, B is equal the set which consists of the state Q0. Yeah. And we denote the state of deterministic finite acceptor Q1, Q2, the set Q1, Q2, and the set which consists of the state Q0. In this point, every state has all transitions defined. The result shown in the following figure is a deterministic finite acceptor. So input state Q0, yeah, output state Q1, which consists of a set of two elements Q1, Q2, which are the states of the deterministic finite acceptor. Equivalent to the so in this figure, yeah, such deterministic finite acceptor is equivalent to the non-deterministic finite acceptor which we started. The deterministic finite acceptor in the figure accepts any string for which delta star of Q0W contains Q1. For the corresponding deterministic finite acceptor to accept every such word W, any state whose label includes the state Q1 must be made a final state. So next we prove the following theorem. Let L be the language accepted by the deterministic finite acceptor Mn with such quintuple Qn, sigma, delta n, Q0, Fn. Then there exists a deterministic finite acceptor Md, which consists of quintuple Qd, sigma, delta d, Q0, Fd, so that the language is accepted by the non-deterministic finite acceptor Mn, coincide with the language which is accepted by the deterministic finite acceptor Md. So we start the proof of this theorem. Given Mn, we use a procedure of non-deterministic finite acceptor to deterministic finite acceptor below to construct the transition graph GD for the deterministic finite acceptor MD. To understand the construction, remember that the graph GD has to have certain properties. Every vertex must have exactly size of alphabet outgoing edges. Each labeled with a different element of the alphabet sigma. During the construction, some of the edges may be missing, but the procedure continues until they are all there. So the procedure NFA to DFA is the following. The first step, create a graph GD with vertex Q0. Identify these vertex as an initial vertex. Repeat the following steps until two more edges are missing. Take any vertex Q1, QG, so on, QK of the graph GD that has no outgoing edge from some letter from sigma. Compute delta star n of QI a, delta star n of QJA, and so on, delta star n of QKA. If delta star n of QI a union with delta star n QGA union, so on, the union with delta star n QK A is equal QL, QM, so on, QN. Create a vertex for the graph GD labeled by this set of states QL, QM, so on, QN, if it does not already exist. Add to the graph GD and add from the set QI, QJ, so on, QK to set QL, QM, so on, QN, and label it in with letter A. Every state of the graph GD whose label contains any GF which is belongs to Fn is identified as a final vertex. If the non-deterministic finite acceptor Mn accepts empty wall lambda, the vertex Q0 in the graph GD is also made a final vertex. It's clear that this procedure always terminated. Each pass through the loop in step 2 adds an edge to the graph GD. But the graph GD has at most 2 in power Q size of Qn element multiply as the size of sigma edges, so that the loop eventually stops. To show that the construction also gives the correct answer, we agree by induction on the length of the input string. Assume that for every word v of the length less than or equal to n, the presence in the graph Gn of a bulk labeled by the word v from Q from the state Q0 to the state Qi implies that in the graph GD there is a bulk labeled by the word v from the state which is denoted by the set, the single set, single element set or singleton set Q0 to state Qi. Consider now any word W is equal VA and look at the walk in the graph Gn labeled by the word W from Q0 to QL. There must then be a walk labeled by the word V from Q0 from the state Q0 to the state Qi, and an edge or a sequence of edges labeled by symbol A from the state Qi to the state QL. By the inductive assumption, In the graph GD, there will be a word labeled by the word B from the state singleton set with consists of states Q0 to the state Q capital I. By construction, there will be an edge from the state Q capital I to some state whose label contains state GQL. Thus, the inductive assumption holds for all strings of the length n plus 1. As it is obviously true for n is equal 1, it is true for all n. The result then is that whenever delta star n of Q0W contains a final state QF, so does the label of the delta star D of Q0W. To complete the proof, we reverse the argument to show that if the label of the image of delta star D of Q0W contains state QF, so must delta star N of Q0W. This completes the proof of theorem. The arguments in this proof, although correct, are admittedly somewhat reverse, showing only the major step. We shall follow this practice in the rest of the course of lecture, emphasizing the basic idea in the proof and omitting minor details which you may want to fill in yourself. The construction in the previous proof is tedious but important. Let us do another example to make so we understand all the steps. Example: convert the deterministic finite acceptors in the following figure to an equivalent deterministic finite acceptor. We have thought non-deterministic finite acceptor. Input state is Q1. We have output state Q0 and our output state Q1. Yeah, we have a loop condition in the state Q0 and the state Q2. Yeah. Since sigma n of Q0 consists of the set of two elements Q0, Q1 is here, must be right, it is correct. Yeah. We introduce the state Q0, Q1 in the graph GD and add the edge labeled by 0 between Q state singleton set Q0 and the state two elements set Q1, Q0, Q1. In the same way, considering delta n of Q01 is equal singleton set Q1 gives us a new state which we denote by singleton set Q1 and an edge labeled by 1 between it and the state singleton set Q0. There are now a number of missing edges, so we continue using the construction of the theorem 202. Looking at the state Q, it is denoted by the two elements set Q0 to Q1. We see that there is no outgoing edge labeled by 0. So we compute delta star n of Q00 union with delta star n of Q10 is equal the state as three element states which contains the states of deterministic finite acceptor Q0, Q1, Q2. This gives us a new state, three elements, new states denoted by three elements set Q0, Q1, Q2, and the transition delta star n of two element states Q0, Q1, 0 is equal state with denoted by three elements, three element states Q0, Q1, Q2. Then using A is equal 1, I is equal 0, G is equal 1, K is equal 2, we get that sigma star n of Q0, 1 union delta star n of Q1, 1 union with delta star n Q2 is equal 1 is equal the states of two elements, states Q1, Q2, make it necessary to introduce yet another state, following two element states Q1, Q2. At this point, we have a partially constructed automaton shown in the following figure. Yeah, input state. Here we constructed the my previous steps. Since there are still some missing edges, we continue until they obtain the complete solution in the following figure. Input state, which is denoted by singleton set Q0, four output states. One important conclusion we can draw from theorem 2 is that every language accepted by non-deterministic finite acceptor is regular. So it's the finish of my lecture. Thank you for your attention. Goodbye, good luck, good health. I wish you anything that is nice for you.